Excellent. Thank you guys so much. Thanks, Golem team. So you guys heard from our Golem program. There's a lot of amazing work being done there on generalist sort of intelligence. We have one other major program that we're working on, which is a little bit different than the sort of generalist intelligence work, because we're looking at a sort of constrained area, which is space robotic swarms. And these sort of swarms, space robotics in particular, are computationally constrained. And also, we're looking at swarm systems, decentralized systems, which mean that we have to look at the other families of bio-inspired sort of computation. Things like embodied evolution or online adaptation, um, the way that swarms kind of work in nature. We have to look at these sorts of things for this program, for this unique sort of challenging scenario. And so I'll go ahead and get into a few of our projects. We have two main projects that we're working on. One of them has sort of two sub-projects within it. And the first one that we are working on is the Modular Space Systems Assembly project. So this project is basically focused on, exactly as it sounds in the name, putting together sort of modular reconfigurable space systems, which are the frontier of spacecraft and space structure design. More and more sort of projects are being done to create these sorts of modular systems. There are several advantages to this. Launches are expensive. Launching a single-use object is very expensive and a single use, so you have to keep launching things. What if instead we could reconfigure the structure online or add to it as time goes on, rather than completely decommissioning that spacecraft and launching another one to replace it? So there are certain advantages to using a sort of modular reconfigurable design. And we see this design cropping up all the time. But um, there are some challenges associated with the assembly of modular space structures. Before we get into those challenges, let's briefly talk about what are the two sort of main paradigms that you could have a structure assemble itself in space, because your options are kind of limited. You mainly have two assembly paradigms. One of them is free flying. So if all the modules can fly, then they can sort of dock and assemble themselves that way. And if they're not capable of free flying, then the other most common sort of paradigm that we see is this magnetic pivoting mechanism. So we have a sub project focused on each of these two paradigms for self-assembly. And our goal with this project is to create an algorithm that can plan the trajectories and control for each of these modules such that any arbitrary configuration can be created. That's our goal for this project. Okay, so the first modality that we talked about was the sort of flying cube modality. This is where the cubes can fly, and the objective here is to assemble into any desired shape. The sort of unique parts of this project are the safety constraints. If the cubes are capable of flying, then they're capable of smashing into each other at a high speed. And so that's sort of the main considerations that we are looking at with this problem. So this project is like a highly constrained optimization problem. I have a couple of demo videos here of some work that we're doing right now. So in this first sort of video, these are very rudimentary and they're not perfect at all yet, but just to give a sort of idea of what we're trying to do. In this first video, our cubes are assembling they're flying together into a P for Purdue, because that's where I'm doing my PhD and where our project team is. And then in the second one, they're turning into a 2x2x2 cube. So some fairly simple sort of shapes, just to give a quick idea of what we're working on. This is, yeah, an early demonstration of this project. Just gonna wait for those guys to come together. Okay, cool. All right, so that's the flying cube sub-project. The second modality, our project lead Ben will talk about that, and that is our pivoting cube sub-project. So go ahead and take it away, Ben.
Hey, I'm Ben. And yeah, so I'm speaking on the pivoting cube subproject. Pivoting cubes are uniform modules that use electromagnetic coupling and decoupling to pivot around each other so that they can reconfigure themselves into any kind of shape. There's a few safety constraints on the available pivoting maneuvers, which makes pivoting an interesting localization and pathfinding problem for each module. The interconnectivity of the modules lends itself to swarm communication and movement, and we're currently developing a reinforcement learning approach that can leverage these swarm attributes to allow for the modules to coordinate and move in parallel with each other. Yeah, so at the right, we visualize the learning process of our current model. And yeah, so we're currently developing that. We look forward to showing you more soon.
Excellent, Ben. Thank you. So those are our two sort of main active modular space systems assembly subprojects. Work is actively ongoing there. The second project that is part of the Aethermorph direction right now is this sort of crowded orbit navigation project. So in the modular space systems assembly project, we talked about sort of this constrained situation where modules need to navigate their relative geometry to assemble properly because there are wrong ways to assemble. This crowded orbit navigation is a different kind of problem. So just to briefly touch on the motivation for this second project, low Earth orbit is very crowded. We've talked about this, I've spoken about this in previous CRCs, but there's this thing called Kessler syndrome where at some point the amount of debris in space is going to start making more debris. And we need methods to navigate this sort of minefield, or I guess like this bullet hell environment that satellites find themselves in orbit. Um, in the first half of 2024, Starlink satellites executed 50,000 collision avoidance maneuvers, and the way that they calculate these collision avoidance maneuvers is very rudimentary. They basically receive a ping from the U.S. government saying collision is imminent and you need to move in one of the six sort of cardinal directions and avoid it. There's a need for scalable, optimal navigation solutions that conserve fuel and work for distributions of spacecraft rather than just single spacecraft. And that's kind of what we're targeting here. So on the right is sort of a brief demo of what we've got so far. Our approach is to use operator learning, um, neural operators. We're using a multi-headed transformer to sort of approximate this neural operator. And the purpose of the neural operator is to generate a set of trajectories for one distribution to go to another target distribution. This sort of distribution to distribution mapping is sort of unique and ongoing area of research in areas like optimal transport and flow matching problems. But it's kind of suited for this circumstance where you need a distribution of satellites to navigate through a distribution of obstacles and wind up in the correct sort of uh, terminal distribution, right? It is uniquely suited to swarms. So this is sort of another thing that we're exploring is this distribution to distribution trajectory optimization in the context of navigating crowded orbits. So this is the second project in the Aethermorph direction.